us, and this is question 12 of the step 1 maths paper from 2018, a probability question. So let's get straight on with it. So we have a bag containing 3 coins. The probabilities of their showing heads are P1, P2 and P3 respectively, and we're going to take a coin at random from the bag, and we want the probability that it shows a head. Now you might just be able to write down the answer here, but if not, we would want to do something like drawing a tree diagram here, and we could say, okay, there's equal chance of each of the coin 1, coin 2 and coin 3 being chosen, and then actually the probability of getting a head for the first one would be P1, for the second one it would be P2, and for the third one it would be P3. So it's fairly easy to see here that the answer of the overall probability of getting a head is just a third times P1 plus a third times P2 plus a third times P3, and we might prefer to write that in this factorized form, a third P1 plus P2 plus P3. It's just the average of the probabilities, and that may be fairly clear intuitively as well. Okay, so in part 2 we says a coin is taken at random from the bag and tossed, returned to the bag, and again a coin is taken from the bag and tossed. We're going to say n1 is a random variable whose value is the number of heads shown on the 2 tosses, and we want to find the expectation of n1 in terms of p, where p is this thing we've done earlier. I'm going to write define to be equal to p there, and show that the variance is 2p 1 minus p. Now, in one sense here, if you studied the binomial distribution, you might just say, obviously, n1 has a binomial distribution with parameters 2 and p, and so that we know immediately that the expectation is just n times p here, which is 2p, and that the variance is n times p times 1 minus p, so it's 2p 1 minus p. But obviously it wants us to show that, so I don't think that's enough for this step question here. I think they'd like us to treat it like a discrete random variables question and say there are different possible outcomes for n, and then if we think about the probability that n1 is equal to n for each of those, well, to get no heads it would be 1 minus p squared, because our new tree diagram here just looks like this. It's a binomial tree where we get a head or a tail, and then we get a head or a tail, and actually because we're just picking one of these coins at random, the probability on each of these tails is just p and 1 minus p, again where p is this average of the 3 probabilities, right? So if you want the full tree diagram, it's going to look something like that. So 1 minus p squared to get two tails here, and then I'm going to have, I need a bit more space to write this down. If I get one head, that's going to be p times 1 minus p plus 1 minus p times p, so that's 2p 1 minus p, and 2 heads is just p squared. So if I want the expected value of n1, I just do 0 times 1 minus p squared plus 1 times 2p times 1 minus p plus 2 times p squared, using the ordinary formula for the expected value of a random variable here, which is that we sum the outcomes times the probability that the random variable takes that outcome. So I've got 0 plus 2p minus 2p squared plus 2p squared, and they cancel out to give 2p. And similarly for the variance of n1, well, for the variance we need to do the expectation of x squared minus the expectation of x squared, written like this, and again our formula for the expectation of x squared is just the sum of x squared times the probability that x equals x. So we'll first work out that, and the expectation of x squared then is 0 squared times 1 minus p squared plus 1 squared times 2p times 1 minus p plus 2 squared times p squared. So I've got 0 plus 2p 1 minus p plus 4p squared, which is 2p minus 2p squared plus 4p squared, which is 2p plus 2p squared, and then we just have to say that the variance of n1 then is, okay, I've said x squared and x here, but I mean the expectation of n1 squared minus the expectation of n1 squared here, so perhaps here I should also have written expectation of n1 squared. So that's 2p plus 2p squared, and the expectation of n1 was 2p, so that's 2p all squared, so that's 2p plus 2p squared minus 4p squared, so that's 2p minus 2p squared, which is 2p 1 minus p as required. Part 3 here, we've got 2 of the coins taken at random from the bag and tossed, and we want n2 now to be the random variable, which says the number of heads that is showing on the 2 coins, and find the expectation of n2 and the variance of n2. So this time we've got a slightly different setup, because so in the previous case we had replacement with the sampling, right? So after I took the first coin, I put it back in, and so the probabilities were the same at the second step now. But in case 3, we've got different possibilities for which coins are going to be used. It might be the first coin and the second coin, the second and the third, or the first and the third, and depending on which is used on the first coin, I'll get a different possibility left for the next one. So actually, if I want to think of the probability that n2 equals 0 here, that's going to be 1/3 times 1 minus p1 times 1 minus p2 plus 1/3 times 1 minus p2 times 1 minus p3 plus 1/3 1 minus p1 times 1 minus p3. Okay, and if you want to think of this in a sort of tree diagram kind of way, what I'm saying here is effectively that the first step, I'm going to choose either coin 1 and 2, coin 2 and 3, or coin 1 and 3. And then from that point onwards, you see I'm thinking of having, and these have all got equal probability, regardless, which 2 coins are chosen out of the 3. And then from that step onwards, each one of these 3 branches gives rise to a tree diagram like this, where I get head, tail, and in this one I'm doing p1 and 1 minus p1, and here I've got p2 and 1 minus p2, and it doesn't matter which way around I write these, obviously. So and then I'm kind of thinking of having 3 copies of that as we go down here. Right? So actually then the probability that n2 is 1, again this time I've got 1/3 times some different options here, and so if it's p1 and p2 other coins, it's going to be p1 1 minus p2 plus p2 1 minus p1. That's one possibility, or I could have the same with coins p2 and p3, or the same with coins p1 and p3. So I've got this slightly complicated looking probability here, but that is the expression that we have, and we might just try simplifying this a little bit. So I can factorize the 1/3 out. What you can see is I've got a p1, a p2 here, a p2, a p3, p1 and p3. So I've actually got 2 p1 plus 2 p2 plus 2 p3. And then I've got a minus p1 p2 minus p2 p1. So I've got minus 2 p1 p2, and the same from the next bit here, minus 2 p2 p3 and minus 2 p1 p3. Okay, I could obviously put a 2 out here as well and collect these 3 together just to be p instead of, well, let's leave it like that I think for now, and we'll simplify it a bit more when we need to. So the final case is that the probability that n2 is 2, i.e. that I get 2 heads, so that's 1/3 times, this is the easiest case, I think, P1, P2, plus a third times P2, P3, plus a third times P1, P3. Okay, so this happens a lot in step questions. We've got some slightly tricky algebra, but once I've written this down, in principle, working at the expectation and the variance is relatively straightforward, because I've just got to use exactly the same formula as before. So the expectation of n2 is 0 times the probability that n2 is 0, plus 1 times the probability that n2 is 1, plus 2 times the probability that n2 equals 2. So that's 0. Don't even need this first expression here, plus this probability that I've got here, 2p1 plus 2p2 plus 2p3, minus 2p1 p2 minus 2p2 p3 minus 2p1 p3, and then I've got 2/3, just factorizing a little bit here, p1 p2 plus 2p2 p3 plus p1 p3, and so actually what we see here is that these terms all cancel out, and we're just left with 2/3 p1 plus p2 plus p3, which is 2p, exactly as before. If you think about this intuitively, I think that should make sense, because there's a lot of symmetry in this problem about which coins are being used, and in fact, if this wasn't a step question, I probably would have just written down that answer 2p immediately here by the symmetries involved in this problem. But I think this is probably the sort of thing we're meant to do here, and it sets us up very well to work out the variance of n2, and again we want to use that formula that it's the expectation of n2 squared minus the expectation of n2 squared, written like this. So we have to work out the expectation of n2 squared. So again, that's just going to be 0 times the probability, or let me write 0 squared, times the probability that n2 equals 0, plus 1 squared times the probability that n2 equals 1, plus 2 squared times the probability that n2 equals 2. And then we've got that that's 0 plus this probability again, so it's this bit is exactly as I had before. Shame you don't get a copy and paste function in the exam. Can make use of it here. And I get, then instead of 2 here, I just get 4/3 times p1 p2 plus p2 p3 plus p1 p3. And so in this case, you see I get something a little bit similar to what I've got before. I've got this 2/3 p term, right, which is the actually, so 1/3 times 2p1 plus 2p2 plus 2p3 is actually 2p, so let's just write that, and then I get minus 2/3 plus 4/3, so I get plus 2/3 times p1 p2 plus p2 p3 plus p1 p3, and that's that. So that means that the variance of n2 squared is this expression here, minus the expectation of n2 squared, which is 2p all squared. So I get something like that, and okay, so I could write this as, so this is, well, maybe I don't need to do too much with this. Actually, I've got 2p minus 4p squared plus 2/3 p1 p2 plus p2 p3 plus p1 p3. Again, I could maybe, I could maybe write this in different ways, but I think that's adequate for what we're looking for here. Right, and then in part 4, we're going to want to show that the variance of n2 is less than or equal to the variance of n1 if with equality if and only if P1 equals P2 equals P3, showing an inequality. It can be easier to show that I want to maybe try to show that the variance of n1 minus the variance of n2, if I can show that's greater than or equal to 0, that will be the same as what I'm trying to show in this inequality, right? So let's just write down what this is. So the variance of n1 was 2p1 minus p, and the variance of n2 is 2p minus 4p squared plus 2/3 times p1 p2 plus p2 p3 plus p1 p3. So this is 2p minus 2p squared minus 2p plus 4p squared minus 2/3 p1 p2 plus p2 p3 plus p1 p3. So my 2p's cancel out, and I've got here left with 2p squared minus 2/3 p1 p2 plus p2 p3 plus p1 p3. And now I'd like to try and come up with a slightly clever argument here. I've got to show that, so I think I need to multiply out my p squared here, right? So remember, p is p1 plus p2 plus p3 all over 3, so p squared is going to be this thing on the top squared over 3 squared, so I'm going to get 2/9 here times p1 plus p2 plus p3 squared, and that's p1 squared plus p2 squared plus p3 squared plus 2 p1 p2 plus 2 p2 p3 plus 2 p1 p3. And then so now if I put this over this other expression, it's currently minus 2/3. If we write that as minus 2/9 times 3 of it, then I'd also get minus 3p1 p2 minus 3p2 p3 minus 3p1 p3. So I've actually got 2/9 times p1 squared plus p2 squared plus p3 squared minus p1 p2 minus p2 p3 minus p1 p3. And this is where you see, if you've done these sorts of arithmetic, geometric mean kind of questions before, you know the sort of thing we're looking for here. We're looking for something like things of the form sort of x minus y squared as our factorizations, and these will be positive, so I'll be able to say they're bigger than 0. And so the sort of thing we're going to be, we think we're trying to get this into the form of here is like p1 minus p2 squared, right? That would be p1 squared plus p2 squared minus 2p1 p2. So if you think about it, if I did, so here's a bit of an aside. Okay, so if I do p1 minus p2 squared, I clearly need to do all the others by symmetry as well. p2 minus p3 squared and p1 minus p3 squared. I get 2 times p1 squared plus 2 times p2 squared plus 2 times p3 squared, and I'm going to get all of the combinations here, minus 2p1 p2 minus 2p2 p3 minus 2p1 p3, and you see this is exactly now double what I've got in here. So actually this thing is in fact just 1/9 times p1 minus p2 squared plus 1/9 p2 minus p3 squared plus 1/9 p1 minus p3 squared, and all of these things are positive expressions, so I can say that's greater than or equal to 0 with equality clearly if and only if each of these brackets are 0, which is when p1 equals p2 equals p3, which is what we're asked to do in the question. And of course we just end up by stating that this does imply that the variance of n1 is greater than or equal to the variance of n2, which is exactly what we wanted to show.